The gunner sat in his compartment, hands not on guns, but on small control grips resembling joysticks, watching through a reflector sight as the fighter closed from 11 o'clock high. This was March the 1944 at the Boeing Test Facility in Seattle, and the exercise was supposed to be theoretical. The B-29 was flying at 360 miles per hour at 25,000 feet. The simulated attacking fighter, another B-29 configured to represent an interceptor's speed and approach angle, was closing at a combined speed exceeding 450 miles per hour. The gunner moved the control grip. A quarter-mile behind him, in the upper forward turret, 4 50-caliber machine guns rotated smoothly, tracking the target with a precision that seemed impossible. The hydraulic system responded instantly. The guns followed his aim point, but more than that, they led the target automatically, compensating for the relative motion between bomber and fighter, for altitude, for airspeed, for the ballistic trajectory of bullets traveling through thin air at 5 miles above the earth. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Boeing engineer watching from behind the gunner made a note on his clipboard. The system was working exactly as designed. This should not have been possible. Every previous bomber in American service, every bomber flying in European skies at that moment, relied on gunners physically manning their weapons, hands on guns, bodies exposed to wind and cold and enemy fire, muscles straining against the forces of high-altitude flight to track fast-moving targets. The B-29 system was different. The gunner sat in a pressurized, heated compartment, looking through a computing sight while hydraulic motors did the physical work of moving tons of steel and ammunition. The system calculated lead, deflection, and range. It corrected for parallax, for the distance between where the gunner sat and where the guns were mounted. It did what human reflexes and human strength simply could not do at the speeds and altitudes where the B-29 was designed to fight. The central question was not whether this system was better than what came before. The question was whether it could work at all, whether hydraulics could respond fast enough, whether analog computers could calculate accurately enough, whether the entire concept of remote-controlled defensive armament was anything more than an engineer's fantasy. Because if it failed, the B-29 program, the most expensive military project in history up to that point, more costly than the Manhattan Project that was proceeding in absolute secrecy, would fail with it. The bomber could not defend itself any other way. Its speed and altitude made manual gun operation impossible. The aircraft was designed around this system. If the hydraulic turrets did not work, 30,000 men in factories across America were building the wrong airplane. Understanding why the B-29's turret system seemed impossible requires understanding what came before. In March 1944, when that test gunner tracked his target with hydraulic precision, the standard for heavy bomber defensive armament was established by aircraft like the B-17 Flying Fortress and the B-24 Liberator. These bombers, flying combat missions over Europe daily, defended themselves with manually operated gun positions. A waist gunner on a B-17 stood in an open window at 25,000 feet where the outside temperature reached 40 degrees below zero. He wore electrically heated flight suits that frequently malfunctioned, leaving men to fight frostbite while fighting the Luftwaffe. He held his 50-caliber machine gun with gloved hands, trying to track fighters that closed at combined speeds exceeding 400 miles per hour. The gun itself weighed 84 pounds. Fully loaded with ammunition belt, it exceeded 100 pounds. The gunner stood in hurricane-force winds, the slipstream tearing at his body and his weapon, trying to lead a target moving faster than his mind could naturally process. The physical demands were brutal. Ball turret gunners, cramped into a rotating sphere beneath the bomber's belly, endured hours in a space barely large enough for a human body. Their guns were power-assisted for traverse and elevation, driven by electric motors, but the gunner still had to physically aim through a computing sight while compressed into a fetal position. Tail gunners sat in isolated positions at the rear of the aircraft, connected to the rest of the crew by intercom, manually operating twin 50s while fighters attacked from dead astern, the most vulnerable approach angle. These systems worked, after a fashion. B-17 and B-24 gunners shot down hundreds of German fighters over Europe. But the cost was terrible. The gunners froze. They succumbed to oxygen deprivation when their systems failed. They were wounded and killed in numbers that made bomber duty the most dangerous assignment in the American military. The 8-hour mission to Berlin and back carried a higher casualty rate than Marine infantry assaults in the Pacific, and the systems did not work well enough. German fighters, particularly the Focke-Wulf 190 and the Messerschmitt 109G, could attack from angles where bomber guns could not effectively track them. They could use speed and altitude advantage to close fast, fire, and break away before defensive gunners could respond effectively. The manual gun positions created gaps in coverage, dead zones, where overlapping fields of fire did not extend. Bomber commanders accepted these limitations because there was no alternative. Manual gunnery was the only system anyone knew how to build and deploy. Bombers defended themselves the way warships had defended themselves for centuries, by placing weapons at key positions, around the vessel and assigning men to operate them directly. The technology had improved from cannon to machine gun, but the fundamental concept remained unchanged. A gunner stood at his weapon and aimed it with his hands and body. The Army Air Forces recognized the limitations of manual defensive armament well before the B-29 entered development. Studies conducted in 1941 analyzed combat reports from the Royal Air Force, which had been fighting over Europe since 1939. The data showed that bomber losses increased dramatically when fighters attacked from specific angles where manual gun positions provided poor coverage. The RAF's solution was to add more gun positions, more gunners, more weight. The Avro Lancaster carried 8 men, 3 of them dedicated gunners. The aircraft bristled with turrets, nose, dorsal, ventral, tail, each manually operated, each requiring a human body positioned at that location in the aircraft. American military planners studied this approach and recognized its fundamental inefficiency. Every gun position required a crew member. Every crew member required oxygen, heat, armor protection, space in the aircraft. The weight accumulated rapidly. A B-17 carried 10 crew members, 5 of them gunners. The aircraft's defensive armament system, including guns, ammunition, turrets, and the men to operate them, represented a significant fraction of the aircraft's useful load. That weight could otherwise carry bombs, fuel, or equipment. But there was a more fundamental problem than weight or crew requirements. The problem was speed. The B-29 was designed from the beginning to fly faster and higher than any previous American bomber. Initial specifications called for a cruising speed exceeding 300 miles per hour at altitudes above 30,000 feet. At those speeds and altitudes, manual gun operation became physically impossible. The forces involved were straightforward physics. A .50 caliber machine gun in a manually operated position had to be traversed and elevated by the gunner's muscles. At 300 miles per hour, the air resistance against the gun barrel and the turret structure created forces measured in hundreds of pounds. A man simply could not move the gun fast enough to track a fighter attacking at closing speeds approaching 500 miles per hour. The mathematical problem was even more challenging. Deflection shooting, leading a moving target so that bullets and target arrive at the same point, requires calculating the angular rate of target motion, the ballistic trajectory of the projectile, the relative speeds of both aircraft, and the distance to target. Human gunners did this instinctively with practice, but their calculations were approximate at best. At high speeds and long ranges, approximate calculations meant missed shots. Ammunition expenditure studies from Europe showed that bomber gunners fired thousands of rounds for each enemy aircraft. Destroyed. The hit probability was abysmal. Engineers at Wright Field in Dayton, Ohio, where the Army Air Forces conducted research and development, calculated that defensive armament for the B-29 would require a fundamentally different approach. Manual operation was inadequate. Power-assisted manual operation, like the electric turret drives used on some B-17 positions, was insufficient. The system needed to be faster, more precise, and capable of complex calculations that human gunners could not perform in combat. The requirement seemed to demand technology that did not yet exist. Remote-controlled turrets where the gunner sat separated from the guns. Hydraulic motors powerful enough to traverse heavy weapons at high speed. Analog computers capable of calculating deflection, lead, and range in real time. A fire control system that integrated all of these components into a unified defensive network. In 1941, when the B-29 specifications were being written, no such system had ever been successfully deployed on any aircraft. The engineers were designing solutions to problems they did not yet know how to solve. The engineer who solved the problem was not a single individual, but a team at General Electric's Schenectady plant in New York, working under contracts that began in 1941. The Army Air Forces had issued specifications that seemed contradictory. They wanted turrets capable of rotating 360 degrees in azimuth and tracking targets through elevation angles from directly below to directly above the aircraft. They wanted response times measured in fractions of a second. They wanted the system to work at altitudes where temperatures reached 60 degrees below zero and air pressure was less than 1/5 that at sea level. And they wanted reliability comparable to the manual systems gunners already trusted with their lives. General Electric's answer was hydraulic power, not the low-pressure hydraulic systems used for landing gear and flaps, but high-pressure systems operating at 1,000 pounds per square inch, 10 times the pressure used in previous aircraft applications. At that pressure, hydraulic fluid moving through precision-machined actuators could generate enormous force in compact spaces. A hydraulic motor the size of a coffee can could rotate a turret weighing hundreds of pounds with the guns, ammunition, and feed mechanisms included. The turret design that emerged was unlike anything previously installed on an aircraft. The upper forward turret, mounted just behind the cockpit, contained 4 50-caliber M2 Browning machine guns arranged in 2 pairs. The entire assembly, guns, hydraulic motors, ammunition feeds, and the armored housing, weighed approximately 650 pounds. Yet the hydraulic system could rotate this mass through 180 degrees in less than 2 seconds. The elevation rate was equally impressive, tracking from level flight to straight up in under 3 seconds. The computing site was the system's brain. Developed by Sperry Gyroscope Company, it was an analog computer using mechanical components, gears, cams, and gyroscopes, to solve differential equations in real time. The gunner looked through a reflector sight showing a illuminated reticle, a circular aiming point with range marks. He turned 2 hand grips to position the reticle over the target. The grips were not directly connected to the guns. They sent inputs to the computer. The computer measured the angular rate at which the target moved across the gunner's field of view. It received airspeed data from the bomber's instruments, altitude from the altimeter, and outside air temperature from sensors. It calculated the ballistic trajectory of 50-caliber bullets at that altitude and temperature. It determined the lead angle needed so that bullets and target would arrive at the same point in space. Then it sent corrected commands to the hydraulic system. positioning the guns not where the gunner aimed, but where the computer calculated they needed to point. The system could control multiple turrets from a single sighting station. The central fire control configuration allowed the gunner in the upper rear position to take control of the upper forward turret if needed. The system could transfer control seamlessly. If one gunner was wounded or his position damaged, another could assume his responsibilities without leaving his own station. This redundancy was impossible with manual gun positions where each weapon required a human body physically present. But the technology created new problems. Hydraulic fluid at high pressure is dangerous. A leak could spray fluid at velocities capable of penetrating human skin and causing severe injury or death. The system required filters to remove contaminants that could jam the precision valves controlling fluid flow. It needed pumps driven by the aircraft's engines, reservoirs to store fluid, accumulators to maintain pressure during high-demand moments when multiple turrets operated simultaneously. Every component had to function at extreme altitude and temperature while subjected to vibration, G-forces during evasive maneuvers, and the shock of guns firing. The computing site required electrical power, stable voltage, despite variations in engine speed and electrical load. The gyroscopes needed time to spin up to operating speed and maintain their orientation. The mechanical computer used precision gears that could bind if contaminated with dirt or ice. The entire system represented thousands of potential failure points, each one capable of rendering the bomber's defensive armament inoperative. Testing began in 1942 at the Boeing plant in Seattle and at Army Air Force's facilities in California and Florida. The early trials revealed problems immediately. Hydraulic seals failed at altitude, losing fluid and pressure. The computing sites vibrated during flight, causing gyroscopes to precess and provide inaccurate data. Turrets jammed when ice formed in the hydraulic lines. Ammunition feeds malfunctioned when the remote control system cycled the guns at rates the feed mechanisms could not sustain. Boeing engineers worked alongside General Electric and Sperry technicians to solve each problem. They redesigned seals using materials that remained flexible at extreme temperatures. They isolated the computing sites from airframe vibration using shock mounts. They added heating elements to prevent ice formation in hydraulic lines. They modified the ammunition feed systems, installing powered boosters that forced belts into the guns, even during high-rate fire. The test gunners were Air Force's sergeants who had trained on manual gun positions. They approached the new system with skepticism. Sitting at a sighting station, controlling guns they could not see or touch felt wrong. The disconnect between their position and the weapons violated every instinct developed through training. When they moved the control grips, there was a fractional delay before the turrets responded, a lag measured in tenths of a second, but perceptible to men accustomed to immediate mechanical connection between hand and weapon. One test gunner, Sergeant Robert Hayes from the Proving Ground Command at Eglin Field in Florida, described his first experience with the system in a report dated August 19, 1943. He wrote that aiming through the computing site felt like watching through a telescope rather than looking down a gun barrel. The reticle floated in his view, apparently disconnected from the aircraft around him. When he tracked a towed target, the system led the target automatically, placing the aiming point ahead of the drogue. His training told him this was correct, that he should lead a moving target. But seeing the computer do it mechanically, without his conscious calculation, was disorienting. Hayes fired at the towed target from various positions as the B-29 maneuvered. The hits came consistently. The strike rate was approximately triple what he achieved with manual guns on a B-17. The computer's calculations were more accurate than his instinctive deflection shooting. The hydraulic system tracked more smoothly than his hands could manage against wind resistance. Every objective measure said the system worked better than what it replaced. But it felt wrong. It felt like the machine was doing the fighting while he merely operated controls. This psychological disconnect troubled training officers. Defensive gunnery required aggressive mindset. Gunners needed to believe they were warriors, not equipment operators. The Air Forces addressed this through training that emphasized the gunner's role as system commander. He might not physically touch the guns, but he controlled them. His judgment selected targets. His skill positioned the aiming point. The hydraulic system and computing sight were tools that amplified his effectiveness, like a telescopic sight amplified his vision. By early 1944, the system was reaching operational readiness. Production B-29s were coming off assembly lines in Wichita, Kansas, in Marietta, Georgia, and at the Boeing plant in Renton, Washington. Each aircraft carried the central fire control system as standard equipment. Each had 5 sighting stations: nose, upper forward, upper rear, right waist, left waist, controlling 4 remote turrets plus a manned tail position with twin 50s controlled locally. The integration of components represented manufacturing precision unprecedented in aircraft production. Hydraulic lines ran throughout the aircraft, precisely routed and secured. Electrical wiring for the computing sites followed complex paths connecting each station to its turret. Ammunition feeds snaked from storage areas in the fuselage to guns mounted in turrets fore and aft. The weight of the entire system, including guns, ammunition, turrets, hydraulic components, and computing sites, was actually less than equivalent manual installations would have required. This seemed impossible until engineers accounted for the eliminated weight. No open gun positions meant no need for armor plate protecting manual gunners. No exposed gunners meant no need for individual oxygen systems, heated suits, and other life support equipment at each position. The central fire control system allowed the entire crew except the tail gunner to operate in the pressurized cabin, reducing equipment weight significantly. The first operational test came not in combat, but in the crucible that preceded combat. The training theater in Kansas, where crews learned to operate the B-29 before deploying overseas. The 20th Air Force, formed specifically to operate B-29s in strategic bombing campaigns against Japan, established training bases where crews flew practice missions and live fire exercises. June 5, 1944. A B-29 from the 58th Bomb Wing flew a gunnery training mission over the ranges at Walker Army Airfield in Kansas. The crew had 30 hours in the aircraft, enough to be familiar with basic operations but still learning the defensive systems. Captain James Patillo commanded the aircraft. His gunners were men transferred from B-17 and B-24 units, experienced aerial gunners adjusting to the new technology. The exercise called for engaging towed targets at various altitudes and speeds. The B-29 flew at 28,000 feet at 290 miles per hour. A twin-engine aircraft towed a target on a cable, 300 feet behind and slightly below. The geometry was standard for aerial gunnery practice. What was not standard was the closing speed. The B-29's velocity combined with maneuvering created engagement conditions faster than any the gunners had experienced in previous aircraft. Staff Sergeant Thomas Chen manned the upper forward sighting station. He had flown 42 combat missions over Europe as a B-17 waist gunner before transferring to B-29 training. His combat experience meant he understood deflection shooting, lead calculations, and the physics of engaging targets in 3-dimensional space. But that experience also meant he had deeply ingrained expectations about how gunnery worked. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Chen tracked the towed target through his computing site. The hydraulic turret responded smoothly, the 450s rotating to follow his inputs. The computer calculated lead automatically, placing the reticle ahead of the target. Chen's training told him to trust the system. His experience told him the lead looked wrong, that the aiming point was too far ahead of the target for the range and angle. He fired. The 50s hammered out rounds at 800 per minute per gun, 3,200 rounds per minute total from the turret. Tracer rounds arced across the sky. Chen watched them converge on the target dead center. The computing site's calculations were precise. The hydraulic system's tracking was smooth. The hits came exactly where the computer predicted they would. Chen released the trigger and tracked another approach. The results repeated. The system was working exactly as designed, delivering hit rates that would have seemed impossible with manual gunnery. In his after-action report, Chen noted that he fired fewer than 200 rounds to achieve hits he would have needed 1,000 rounds to accomplish in his B-17. The computing site eliminated his need to estimate lead. The hydraulic system eliminated the physical effort of moving guns against wind resistance. The technology performed as advertised. But something else happened during that training mission that revealed the system's true revolutionary nature. As Chen tracked his target, Captain Petillo ordered evasive maneuvers. The B-29 rolled into a 30-degree bank and pulled through a climbing turn. In a B-17, such maneuvering would have thrown waist gunners off balance, making accurate fire impossible. Chen, seated at his sighting station in the pressurized cabin, barely felt the maneuver. The gyroscopes in his computing site maintained stable reference. The hydraulic turret compensated for the aircraft's motion. He continued tracking and firing as if the bomber flew straight and level. The system isolated him from the chaos of evasive flight. The first B-29s reached combat theaters in April 1944, deploying to bases in India and China under the 20th Bomber Command. The missions began in June with raids against Japanese targets in Thailand, Manchuria, and eventually Japan itself. The crews flying these missions were guinea pigs for untested technology. Every aspect of the B-29 was new: its engines, its pressurization system, its range, and critically, its defensive armament. The hydraulic turret system faced its first real test on June 15, 1944, when B-29 struck the Imperial Iron and Steel Works at Yawata on the Japanese home island of Kyushu. 68 bombers launched from bases in China, flying a 16-hour round trip over water and enemy territory. Japanese fighters intercepted them. For the first time, American gunners engaged enemy aircraft using the remote-controlled fire control system under actual combat conditions. The encounter revealed immediately that the system provided capabilities manual gunnery could not match. Japanese fighters, particularly the Kai-43 Oscar and the newer Kai-61 Tony, attacked using tactics developed against B-17s and B-24s over the Pacific and Southeast Asia. They approached from angles they knew created gaps in manual gun coverage, expecting to find similar vulnerabilities. What they found instead was defensive fire from unexpected directions, turrets that tracked faster than their attack speed, concentrated fire from multiple guns controlled by single gunners. Staff Sergeant Henry Irwin, a radio operator aboard a B-29 named City of Los Angeles, described the engagement in a letter to his family dated June 20, 1944. He wrote that the upper gunner called out a fighter approaching from 10 o'clock high, a classic attack angle exploiting the gap between nose and dorsal positions on conventional bombers. The gunner engaged with the forward upper turret, tracking the fighter through its attack run. The 450s fired a 3-second burst. The fighter's engine began trailing smoke. It broke off without firing its weapons. Irwin noted that the entire engagement, from first sighting to the fighter's withdrawal, lasted perhaps 8 seconds. The hydraulic system's response time made the difference between being attacked and driving off the attacker before he reached firing position. The Japanese recognized quickly that B-29s defended themselves differently than previous American bombers. Intelligence reports captured after the war showed Japanese fighter pilots describing the B-29's defensive fire as appearing from all directions simultaneously, and noting that gun positions could not be identified by observing the aircraft's external appearance. The remote turrets meant Japanese pilots could not predict gun coverage by looking at the bomber. There were no obvious open gun positions to avoid. The guns appeared to fire from locations where no gunner was visible. This psychological element proved as important as the technical superiority. Japanese fighter pilots had learned to attack B-17s and B-24s by studying their defensive patterns, identifying blind spots and approach angles where manual gunners had difficulty tracking. The B-29 provided no such pattern. Every approach angle was covered. Every attack met immediate, accurate defensive fire. Fighter pilots reported that B-29 gunners seemed to anticipate their attacks, bringing guns to bear before the A fighter reached firing position. What they were observing was not anticipation, but simply faster response times. The hydraulic system moved guns to track threats more quickly than human muscles could manage manually. By August 1944, B-29s were also deploying to the Mariana Islands, Saipan, Tinian, and Guam, recently captured at significant cost. These bases put Tokyo within range for regular bombing missions. The aircraft flying from the Marianas represented improved production models with modifications based on early combat experience. The hydraulic systems had been refined. Seal materials had been improved. Computing sites had been recalibrated based on actual combat data, showing typical engagement ranges and closing speeds. The crews who flew these missions experienced defensive armament in a fundamentally new way. Gunners sat in their stations watching through computing sites, while hydraulic systems did the physical work. They were insulated from the violence happening outside their pressurized cabin. They aimed and fired, but they did not feel the wind, the cold, or the physical strain that had characterized aerial gunnery in every previous bomber. This created unexpected psychological effects. Some gunners reported feeling disconnected from the combat, as if they were operating a simulator rather than fighting for their lives. The mechanical nature of the system, the smooth hydraulic response, the precise computer calculations, these created an emotional distance from the immediacy of combat. When a gunner in a B-17 fired his manually operated waist gun, he felt the recoil through his hands, saw the gun barrel vibrating, smelled the cordite, experienced the physical reality of shooting. The B-29 gunner experienced none of this. He moved control grips and watched turrets respond through a sight that might have been showing a training film for all the physical feedback it provided. Technical Sergeant Robert Mayfield, who flew 35 missions from Tinian between November 1944 and May 1945, described this disconnect in his post-war memoir. He wrote that shooting down his first Japanese fighter felt strangely impersonal, like passing a test rather than killing a man. He had tracked the fighter through his computing site, placed the reticle ahead of the target as trained, and fired. The system calculated everything. The hydraulics positioned the guns. The computer led the target. His role had been simply to identify the threat and initiate fire. When the fighter began trailing smoke and fell away, Mayfield felt he had operated a machine correctly, rather than fought an enemy personally. But this emotional distance came with a practical benefit: reduced psychological trauma. Studies conducted after the war by the Army Air Force's Surgeon General's Office compared combat fatigue rates between B-17 and B-29 gunners. The B-29 gunners showed significantly lower rates of combat stress reactions, despite flying missions of comparable danger. The insulation from physical discomfort, the reduction in feelings of personal vulnerability, and the confidence inspired by superior equipment all contributed to better psychological resilience. The Japanese response to the B-29's defensive capabilities evolved slowly. Fighter tactics changed to emphasize head-on attacks where closure rates were highest and where even the hydraulic system's fast response times were challenged. Pilots attempted to engage from directly above or below, exploiting the limited elevation and depression angles of the turret systems. Some units tried ramming attacks, recognizing that conventional gunnery could not guarantee kills against well-defended bombers. But these tactical adaptations could not overcome the fundamental disparity. The B-29's defensive system represented engineering solutions to problems the Japanese had not solved. Japanese bombers like the G-4M Betty relied on manual gun positions that left crews exposed. Japanese fighters lacked the armament to engage B-29s effectively from outside defensive gun range. The technological gap was not merely in the hydraulic turrets themselves, but in the industrial capacity and engineering sophistication required to design, produce, and deploy such systems. By March 1945, when B-29s began flying low-altitude incendiary raids against Japanese cities, the defensive fire control system had proven itself thoroughly. Loss rates from fighter attacks were substantially lower than early predictions had estimated. The primary threats to B-29s were anti-aircraft artillery and mechanical failures, not enemy fighters. The hydraulic turrets, the technology that had seemed impossibly complex in 1941, had become reliable operational equipment trusted by crews flying combat missions into the most heavily defended airspace Japan could create. The men who had designed the system, the General Electric engineers working in Schenectady, the Sperry technicians developing computing sites, never saw combat. They fought their war with slide rules and test benches. But their contribution was measurable in empty seats at Japanese air bases, in fighters that returned damaged or not at all, in bombers that completed their missions despite determined enemy opposition. The B-29's hydraulic fire control system represented more than technological innovation. It represented a philosophical shift in how America approached industrial warfare. The system assumed that complex mechanical solutions were preferable to human endurance. It assumed that engineering could overcome limitations that previous generations had accepted as inherent to aerial combat. It assumed that American industry could manufacture precision components at scale, that hydraulic systems operating at extreme pressures could be made reliable, that analog computers could perform calculations in real time. Every assumption proved correct. The system worked. Not perfectly. Hydraulic failures occurred, computing sites malfunctioned, turrets jammed, but with reliability sufficient for combat operations. The B-29 program produced 1,739 aircraft by the end of 1945. Each one carried the hydraulic turret system as standard equipment. The General Electric plants produced thousands of turret assemblies. Sperry manufactured computing sites in quantities that would have been unimaginable in peacetime. The entire supply chain, from hydraulic seal manufacturers to ammunition feed system producers, scaled up to support a weapons system that had not existed 4 years earlier. Post-war analysis by the United States Strategic Bombing Survey examined B-29 loss rates and determined that the defensive fire control system had contributed significantly to crew survival. The survey calculated that B-29 gunners achieved approximately 3 times the hit probability of gunners using manual systems in comparable combat conditions. This did not mean B-29s were invulnerable. 394 were lost in combat operations, but it meant they were substantially more survivable than they would have been with conventional defensive armament. The psychological impact on Japanese defenders was documented in interrogations and captured documents. Fighter pilots described the B-29 as defending from all directions and impossible to approach safely. Ground observers reported that defensive fire from B-29 formations appeared continuous and coordinated, creating a protective barrier that Japanese fighters could not penetrate without severe losses. The reputation of American technological superiority, already established through industrial production capacity, was reinforced by weapons systems like the B-29's remote-controlled turrets. The legacy extended beyond the war. Post-war bomber designs incorporated lessons learned from the B-29 program. The Boeing B-50, essentially an improved B-29, retained the hydraulic fire control system. The Convair B-36, designed to strike the Soviet Union from American bases, used an evolution of the same technology with even more powerful hydraulic systems and improved computing sites. The Boeing B-52, which entered service in 1955 and remains operational today, used remote-controlled defensive turrets until those systems were finally removed in 1991, after nearly 4 decades of service. The engineers who developed the original system moved on to new challenges. General Electric's expertise in high-pressure hydraulics informed post-war development of industrial systems and aircraft flight controls. Sperry's analog computing work evolved into early digital fire control systems and eventually into general-purpose computing. The manufacturing techniques developed to produce hydraulic turrets at scale influenced precision engineering across American industry. For the gunners who sat at those sighting stations tracking targets through computing sites while hydraulic motors positioned guns they could not see, the experience changed how they understood their role. They were not traditional warriors wielding weapons through physical strength and courage. They were system operators, trained to use complex technology to multiply their effectiveness. This shift from warrior to operator, from physical combat to technical proficiency, would characterize American military development throughout the Cold War and beyond. The morning in March 1944, when that test gunner tracked his target at 400 miles per hour, watching hydraulic turrets respond with mechanical precision, marked a turning point in aerial warfare. The technology worked. The impossible system was possible. The engineers had solved problems that traditional military thinking said could not be solved, and in doing so, they created a bomber that could defend itself in ways no previous aircraft could match, flown by crews who trusted technology to do what human strength alone could not accomplish. The cost of that truth was measured in Japanese fighters that never returned, in B-29 crews who completed their missions and came home, and in the recognition that modern warfare belonged to nations that could harness industrial capacity and engineering sophistication to create weapons systems their enemies could not match. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.